Hello everyone, my name is Harris, and in this video we're going to quickly go over number 7 on the exam, and it's kind of the I think I want to say it is the fifth kind of main problem on our exam, or our fifth kind of regular problem, and it's known as the knapsack problem. So in the knapsack problem, we're given weights and values of n items. So in our example, those items are going to be a cell phone charger, a laptop charger, a tent, medicine, instant food, water bottle, umbrella, and flashlight. Those are in the table on the top right, and they're also in the table on the left, which was given to us. But the difference is in the table on the top right page is the cell phone and charger. They are to be taken together. So in that table, I decided to go ahead and put that in there and put them together, so you can see the actual value in weight. And so our goal is in this problem is to select the optimal number of items with the maximum value without exceeding the maximum weight, which was given in the problem of 7 for this one. So in this knapsack, I just want to point out that we're not able to break up any items, and this is actually kind of crucial to making this problem, because if we were able to break up the problems, it would change the runtime, as well as dynamic programming wouldn't really be needed, or wouldn't be necessary, I'll say. So in a problem in a video I did before, we noted that dynamic programming has two main characteristics. A problem kind of needs to meet in order for dynamic programming to be necessary. The first one is optimal substructure. And we will consider all subsets of items, and there will be two cases for each item. So the first case is that the item will be included in the optimal subset, and the second case is that it won't be included in the optimal subset. And dynamic programming is used to show that the maximum value of n items that can be obtained is shown by the max of the maximum value obtained by n minus 1 items and the weight, or the value of the nth item plus the maximum value of the n minus 1 items and the weight, and then minus the weight of the nth item. So there are two cases, like I said, and I have the formula on the right side in the middle of the two tables. This is a recursive problem that works. It's dynamic programming works great for solving these recursive problems. So the two cases is V by W equals VI minus 1 W if WI is greater than W. So basically, this case, I'm going to highlight a few things. I'm pretty sure you can see it. I have a 0 highlighted on the table on the bottom right. This is where the nth item cannot be included because it's greater than. So, example 4 here, right here, or even right here, cannot be included because it has a weight of 4, and our max weight at this point is 2. So recursively, we go down and grab, we check the problem beforehand. That's the n minus 1, and so forth. So the second problem, we either include it or we don't. But like I said, this is V I comma W equals max VI minus 1 W, and or VI minus 1 W minus WI plus VI, which includes the nth item V. So for example, that one is chosen for example 6 and 7 down here on the right hand side. But first, let's just kind of walk through. I'm going to walk through maybe like 1 or 2 of these on the table. So for this one, it's 0 because we have a weight of 2. I also want to point out in this problem, we can only use each item once, and Yeah, that's important. But so here we just look at, we only have this one item, the top row, and it has a weight of 2. So it cannot fit in weight of 1. So we move to the next, weight of 2, 130, and because we only have that one problem, we know that it fits in all of these along this row, which gives us 130 for the rest of them. But we don't have any other items yet, so that's where we kind of stay at. So the next row, we see we have 0, 0 again because we have no weights of just 1 yet. And then we move on to the next 2 where we can only put in item number 1 with the weight of 2. And then 4, we finally get the chance to put in 370. And the reason we put in 370 over 130 is because it has a higher value. And now on 6 and 7, we're able to fit a weight of 6 and a weight of 7, which item 1 and 2 add up to weight of 6, and their value adds up to weight 500. So I just wanted to go through a few of those. So we get a total maximum value of 100. Of 700, and this I want to say that this can be achieved through a few different variations as seen in the table above. Also, I wanted to show a programming example. I just thought, just to kind of add in there, the main thing to know is that this right here is where the cases are tested that we saw. We iterate through each item from left to right, kind of as we did in the table on the last page. And first, we check if the item's weight is less than or greater than, is greater than or less than or equal to the maximum weight, the current weight of the knapsack, and just like we saw in the formulas on the last page. So that's it for the knapsack problem. Thanks everyone for watching.